Today we have Ellen Vitercik giving a talk on sample complexity of revenue maximization. Ellen is a first-year PhD student in the CS department, and she works with Rademacher and Thomas Sandholm. Her interests are in learning theory and also in mechanism design.
All right, thank you. Right, so I'm going to be talking today about sample complexity of revenue maximization, specifically in a hierarchy of deterministic combinatorial auctions. Right, so the setting here is that we have multiple bidders and multiple items. So this is what's called a combinatorial auction. And the complexity here is that the amount a bidder values a bundle of goods may not equal the amount she values the sum of the individual goods in that bundle. So in the most complex extreme of a combinatorial auction, the auctioneer would allow the bidders to submit, valuations or bids for all 2 to the n bundles. And then the auctioneer would solve for the best allocation, whatever best might mean in this scenario. So they're a very expressive auction format, but they're also very complex. But despite this complexity, they have been fielded in the real world. So for example, the government has proposed using combinatorial auctions to allocate wireless spectrum to providers. Combinatorial auctions have been used in the sourcing domain. For example, Thomas Sandholm, one of my collaborators, has fielded combinatorial auctions for sourcing. One of the first proposed applications of combinatorial auctions was for airport time slot allocation. And combinatorial auctions are natural for building development. For example, I heard that the office space in Gates was allocated via a combinatorial auction. And this makes sense because a professor might especially value an office that is near her lab, for example. And even before combinatorial auctions made it to computer science departments, they were used in property sales.
What was the currency used in the Gates auction?
Oh, there was no money. I think from what I've heard, the bidders the faculty and students just rated how much they would want an office. So no money involved. And so combinatorial auction design falls under the category more generally of mechanism design. And a mechanism or auction designer is in charge of determining 2 functions. They have to determine the allocation function, who gets what based on the bids, and they have to determine the payment function. So what do the bidders pay based on their bids and on the allocation? And these functions could be almost anything you could imagine. So for example, I could give the goods to the highest bidders and charge them their bids. I could choose a random subset of bidders to allocate the items to and charge them nothing. But a lot of the time, the allocation and the payment function in conjunction will incentivize the bidders to lie about their valuations. But as is typically done, we're going to restrict the design space to those auctions we can prove are strategy proof. So by strategy proof, I mean that it is in the mechanism designer's best interest to report their bids truthfully. That's the utility maximizing strategy.
It's in whose best interest?
It's in the bidders. I might have said misspoke. It's in the bidders' best interest to report their bids truthfully. So this isn't, I'm not going to get into why, but this isn't as harsh as a restriction as it might seem. And it allows the bidders to have a very easy bidding strategy, just report their bids truthfully. And it's easier for the designer to analyze all possible outcomes. So before I get to multi-item auctions, I'm going to start with single-item auctions, which we know much more about. And one of the best known single-item auctions is the second price or Vickery auction. So here, the single item goes to the highest bidder, and that winner pays the second highest bid. So here, we would give the carrot to Nina and charge her $3, which was Tuomas's bid. And it's really simple to prove that this auction, the second price auction, is strategy proof. It won't necessarily maximize revenue, but it will maximize the social welfare of the bidders. But we are the auction designers in this research project, and we want to maximize revenue. So that is our goal. Okay, so now to move on to the more general multi-item case, I'm just going to describe a few assumptions we make. So as is almost ubiquitous, we assume that the bidder's valuations are drawn from some distribution, D, and oftentimes it's assumed that this distribution is known by the auction designer. And this manifests itself in the auction design because the allocation and payment functions are often explicitly dependent on what D looks like.
Can I ask a simple question?
Yes.
Well, what if you went back to the simple case of non-combinatorial auction, and you changed so you said that was, the Vickery auction was maximizing the social welfare?
Right.
But what if you said, I want to maximize revenue?
Right,
Is it
so
the same solution again?
it's close to the same solution. So Roger Myerson, the Nobel Prize winning economist, discovered the strategy-proof revenue maximizing auction, which is very similar to the second price auction, but on what are called virtual valuations, which are kind of a transformation of the bid space. So it still does look like second price, but it's not going to be exactly the same. It's going to depend actually a lot on what the distribution D looks like.
So you're generalizing that, yeah, in this work?
Yeah, you could say that. Yeah, we're generalizing. We're calling on techniques from Meyerson's auction. Okay. So now going back to multi-item auctions. So there are a few design challenges here. So we said that it's often assumed that maybe D is known by the auctioneer in advance. But in multi-item auctions, D might be doubly exponential. So even if we assume that somehow there is a way for the auctioneer to know D in advance, it's not even really feasible to assume that he could have some concise description of D. Moreover, it's NP hard to determine the revenue maximizing auction if you even know D in advance. So what are some solutions, potential solutions we can propose? Well, for example, we could draw samples from D instead. We could assume maybe we have sample access to D. You know, this might come in many different forms. Maybe we have some prior purchase history of the bidders. Maybe we conduct, consumer surveys. It doesn't really matter exactly how we have samples from D, but let's assume that we can sample D. And then it is hard to find the revenue maximizing combinatorial auction, but maybe we can fix a rich subclass of combinatorial auctions, and we can learn the revenue maximizing auction in that subset. And this will be revenue maximizing in expectation over D with given samples drawn from D. This would be the goal if we could do this. And in fact, this is a central problem that has been addressed in the field known as automated mechanism design. We have samples drawn from the bidder's prior distributions, D, and then we do a sophisticated search over some subclass, some rich subclass of combinatorial auctions, and look for the best one in that subclass. But until now, there was no theory that related the performance of those auctions on a sample to their expected performance over the distribution. So it could be that you did this search and the best auction over the sample did very badly on the distribution. Okay, so, but in this work, actually, we're not going to just look at one rich subclass. We're going to look at an entire hierarchy of combinatorial auction subclasses. And we're going to ask the question, how many samples do we need in order to learn the best auction in that class? And along the way, we gain interesting insights into the structure of these auction classes. So I'm going to talk about this hierarchy and then talk about our sample complexity results and the tools we use to derive those results. Okay, and now some notation so that I can talk about these multi-item auctions. Here's a simple example I'm going to use throughout of some valuations Nina and Tuomas have for 2 goods. And so in this example, there are 3 to the 2 possible outcomes. There are 2 items, and each item can go to either Nina, Tuomas, or nobody. So there are 3 to the 2 possible outcomes. And I'm going to denote these outcomes by this vector. So the carrot goes to Nina, and the tomato goes to Tuomas in this example. Okay, and now I'm going to describe a very simple and natural, well-known generalization of second price auction, that classic strategy proof auction for the single item case. I'm going to describe a generalization to the multi-item case. And this is going to serve as a kind of base case by which I can build this hierarchy of combinatorial auctions. And to do this, I need to define the social welfare of an outcome, which is a term I already used. But here's what it means for a multi-bidder case. So the social welfare of an outcome is just the valuations of the bidders for that outcome. So it's pretty simple. And let's say that O star maximizes the outcome. I'm also going to need the social welfare without any one bidder of an outcome. So I'm just summing over all bidders except some bidder I here. And let's say that O to the negative I is the outcome that maximizes the social welfare without any one bidder's participation. And note that O star definitely need not equal O to the negative I. Okay, so this natural generalization, what I'm going to do, the allocation is to give the allocate the social welfare maximizing outcome. And then, for example, what are the payments? Well, Nina, or respectively Tuomas, is going to pay the social welfare of the other bidders without her participation, the highest social welfare achievable without her participation in the auction, minus the social welfare of the other bidders given her participation in the auction. So you can think of this as measuring the difference between how much happier the bidders would have been if Nina hadn't participated in the auction. And this is called the Vickery-Clark-Groves mechanism. So it is strategy proof, and it's definitely not revenue maximizing. So let's just go through this example.
In this
Yes.
example, are you going to start discussing the...
Oh, I've got to go through what it would be, what would happen in this example. So in this example, the social welfare maximizing allocation would be that Nina gets the carrot and Tuomas gets the tomato. That one this has a social welfare of 150. And that best outcome in this very simple example, the best outcome without Nina's participation in the auction is kind of obviously that Tuomas would just get both items. He gets what is called the grand bundle. And Nina then pays how much does Tuomas value his allocation without her in the auction, minus how much does he value his allocation given her participation in the auction, which is $0. And since our goal is revenue maximization, this is kind of unfortunate because Nina values her allocation by $1. So it would be really nice if we could somehow if we could somehow adjust this auction to force Nina to pay 99 cents, that would be great.
Sorry, it
Yes.
seems at least the valuations are monotone.
So in this, we are assuming that the valuations are monotone. Mhm. So how do we get the bidders to pay more? Okay, so one of the mechanisms I'm going to introduce for getting the bidders to pay more is called outcome boosting. Okay, so we take an outcome. For example, Nina gets empty set, Tuomas gets grand bundle. The value of this is just the sum of the bidders' valuations for their allocation, which is 50 cents. And then I'm going to boost this by 99 cents. And hopefully this will become a little clearer. What do I mean by boost? But basically what I'm saying is that when you're doing this maximization over outcomes to figure out what should the allocation of this auction be, you're going to take the boosts into account when you're doing this maximization. Okay, so you can think of this as saying that we're making it 99 cents more likely that this is the outcome of this auction. So in this example, with this boosted outcome, the outcome actually doesn't change because the value of this outcome is still 150. And when I boosted this outcome only got boosted to 149. So it's not going to be the outcome of this auction. And of course, without Nina's participation, Tuomas is still going to value this outcome the most. In fact, it is the outcome I boosted. So nothing is going to change. But what is very interesting is that now the payment function is going to change. So the way these auctions work is that you include the boost. We boosted the best outcome without Nina's participation, and we include that boost in the payment. So now Nina is going to pay the boosted amount that Tuomas likes this outcome, minus the amount he likes the actual outcome of the auction. So this is going to be 99 cents now. So that's great for us. Like, we've now forced Nina to pay almost as much as we could expect her to pay. And the amazing thing is that even with these boosts, the auctions remain they remain strategy proof.
I'm not sure. Say, how do you actually take, I guess, a distribution and then get the payment structure for the outcomes? I'm sorry, I can't infer from this example the general procedure.
Okay. So actually, maybe this next slide will help. So the auctioneer, the mechanism designer, has samples from the distribution. And somehow, from those samples, he is going to figure out how to boost these outcomes. He's going to learn how to boost these outcomes. He's going to write an algorithm based on these samples to boost these outcomes. Then he's going to take a bid. These bids look like the samples he just optimized over. He's going to take a bid, and then from that bid, he's going to compute the social welfare of every outcome, including the boost, in order to figure out what should the outcome of this auction be. So social welfare it is a sum over valuations. It's a sum over bids, since this is strategy proof. And then we can compute the social welfare of the best outcome. It's just another maximization problem over the bids. We just compute the best social welfare without any one bidder's participation, plus the boosts we decided on before we took the bids. We decided these boosts based on the sample. And then we can compute the social welfare, of course, over the bids that we got for the outcome that we chose. Does that clear that up?
I have one question. Is it like always strategy proof, no matter what the boosts are?
Yes.
Even the boosts depend on the bids?
So the boosts you decide on before you see the actual bids.
Do the participants know the boost values?
Yeah.
Yeah, they can know the boost values. And it's still strategy proof.
And it's strategy proof for that particular round. It doesn't mean that if the same participants participate in further rounds, that by altering what they do in this round, they can improve
Yeah, not necessarily, right, Thomas? It doesn't necessarily.
There's no rounds.
No, but you mentioned basically you get samples from the previous instances of the same option.
I think you're asking two good questions there. One is that, including the previous question you asked, there's a distribution. We are not saying that the distribution comes from previous auctions. There just is a distribution from which you draw samples. Maybe that comes, as Ellen said, from surveys, or maybe it's somehow inferred from other auctions or previous similar auctions. There is a valuation distribution, which is the standard assumption. And then we are going to decide one auction, we're going to run that one auction, the world ends. There are no rounds. Which is standard assumption in mechanism design. So it's typically mechanism design is a single shot setting, and we're in that framework. And then you were asking about the algorithm, given the samples, how do you actually design the right boosting? Our theory here is going to be agnostic to that. So there's prior work that we've done and other people have done on that question, but we're going to be agnostic to that. So Ellen is not talking about what is that algorithm that's going to take those samples and give you the boosting. There are other algorithms for that, but that's a long story.
That's the field of automated mechanism design. Okay. Are there any other questions?
So the boost is for every subset of items?
So it's for outcomes. So an outcome.
Every partition of items.
Yeah, every partition of items. And it need not even be a partition. It could be that some items don't go to anybody. Anupam.
Alan, should I just think of the boost as just creating a virtual player and giving them some sort of, this is the valuation of this virtual player for the outcome?
Yeah, I guess you could think of it that way, though it would be a bid on an outcome as opposed to a bid on a bundle of goods. So we're boosting outcomes. That's the important thing, not bundles.
You know, it almost makes sense with the virtual player, if the boost only depended on those items that weren't given to anyone, then you can imagine they were given to the virtual player.
But she's saying outcomes are, it's not really a partition. So an outcome is just, I might value you getting something as well. Perfectly reasonable thing to have valuations on.
Yeah.
Okay.
So you're always adding the lambda to the SW.
Yes.
Except, so that's kind of what Anupam was saying. It's just modifying the SW by this other
By a lambda.
artificial boost parameter. But then you're not, it's not quite the same because you've got the SW minus I.
Yeah, so maybe that's not the way to, so this is an outcome. This is an outcome, the best social welfare maximizing outcome without a bidder's participation. It's an outcome and we can boost that outcome. So it's the boost associated with that outcome, the best outcome without a bidder's participation. Yeah.
I'm also a bit confused about strategy proofness. Like even in the single item case, if I have the higher value, but we boost the other guy's value, so the outcome where the other guy gets the item, and then so the outcome would be they get the item and pay my valuation, which is the actual valuation. Like if the payments and the outcome depend on these boosts,
So the boost would be subtracted out from, so you're saying like the boost, maybe they'd have to pay more.
They would have to pay, they would win when they were not supposed to win because we boosted their value, like the outcome where they get the item. And then they end up paying let's say the outcome where I get the item wasn't boosted. So they just pay my value, it's just second price auction. But they pay my value, which is more than their true value. So in some sense, maybe they want to underbid to lose the auction.
So no, I think they would actually pay, zero. Well, let's talk about this afterwards maybe, because I'm starting to run a little low on time. But I think that the lambda terms would actually cancel out in that case. But yeah, we can maybe talk about it afterwards. Okay, in any case, I'm just going to kind of, here are the outcome and the payment functions expanded. So I just expanded the social welfare. And now one other thing we can do to modify the bid space is we can add a weight per bidder. So by that, I just mean that you multiplicatively increase the weight, the bids of any one bidder. So for example, here, the weight is calculated in as blowing up the one bidder's bid by some multiplicative amount, and then the weight is going to factor in kind of as you would expect in the payment function. Okay. So these are, and I'll mention also, these are known as affine maximizer auctions, which were introduced by Roberts in 1979. And they are the highest. They are the highest class in our hierarchy. They're the most general because the weights and the lambda terms can be anything. And now, so I said we introduce a or we consider a hierarchy. We consider sample complexity over a hierarchy. So some of the classes under affine maximizers in this hierarchy are virtual evaluation combinatorial auctions. It doesn't really matter too much what is here, but basically what we're doing is we're restricting what the lambdas can look like. So we're kind of decreasing the complexity of the possible lambda terms. And there are also lambda auctions, so we can set the bidder weights just to be 1 across all bidders, but we can still let the lambdas be anything. We also consider mixed bundling auctions with reserve prices, where the weights are still 1 and the lambdas are forced to be 0, except for those outcomes where one bidder gets all items. One bidder gets a grand bundle. So there are n-many such outcomes for n bidders, and we boost all of them. And we can also introduce reserve prices. We consider item-specific reserve prices where an item isn't sold unless a bid exceeds that item. That item reserve price.
Would it be the sum of the reserve prices of all
The sum of the reserve prices, because we show actually exponential lower bound for how many samples you would need to learn bundle-specific reserve prices. And the final class is mixed bundling auctions, which are just the same as those with reserve prices, but without the reserve prices. Okay. And so we consider sample complexity. We consider how many samples would I need to make sure that whatever auction I find that maximizes revenue over the sample, it has almost optimal revenue over the distribution. So I'm just going to kind of formalize that question and then show our results. So, so the goal, we get these samples, and we want to optimize the lambda terms and the W terms given a sample. This is the problem that is addressed in automated mechanism design. That's where those algorithms come from for doing this problem. And what we want is that the auction with the best revenue over the sample has almost optimal revenue with respect to the distribution. And moreover, sometimes it's hard to optimize over the space of, over these auction classes. So affine maximizer auctions are a very rich class of auctions, so it's hard to optimize over them. So we would also like that any approximately optimal auction over the sample has approximately optimal revenue with respect to the distribution. And gleaning over some details, like basically we will get both of these bullet points if we can ensure that S is large enough that with high probability, the empirical revenue of an auction is close to the expected revenue of that auction. And more specifically, how large does S have to be to ensure that the empirical revenue, where rev sub A of V is you'd have this bidding instance, this vector of valuations, and it's A is a specific auction, and so rev sub A of V is the revenue of the auction A on the bidding instance V. How big does S have to be to ensure that this empirical revenue is close to expected revenue for all auctions in the class? If we can guarantee this for all auctions in the class, this is known as uniform convergence in learning theory, then we can get these bullet points. Yeah. And I'm leaving out a couple of things, like for example, we can only do this with high probability. And so here are sample complexity results that we derived for the hierarchy of auctions. And I'll just point out a few things before I talk about, I'm only going to talk about a couple of these results. So for these exponential upper bounds, we got nearly matching exponential lower bounds. They're very complex classes of auctions. We used Rademacher complexity to understand these auction classes, and we used pseudo-dimension to understand these auction classes. Okay.
Alan, are your prices all integral? We have U as a parameter, the maximum revenue achievable.
It doesn't need to be integral. It's just an upper bound
The
on.
ratio of the highest to the lowest revenue? Or?
I guess the revenue can be from 0 to U on an auction.
Then I can scale down everything by as much as I want, right? So I'm not quite sure I understand what U.
Well, it's like divided by epsilon everyone, right? So
So the error was absolute.
yeah,
So the error was absolute.
Yeah, thank you. Okay, so the first class, I'm going to talk about sample complexity for the class of affine maximizer auctions, for which we use Rademacher complexity. And so let's see. I'm just going to, so here, just to remind you, it's the top class. That's you can see our sample complexity result there.
What's the difference between those? It's too hard to parse it. They all look the same to me, but maybe I'm missing an epsilon somewhere.
So let's see. Actually, these are the same because we can use, if we have an upper bound for affine maximizer auctions, then we can use that upper bound also for lower classes in the hierarchy. And then our lower bounds differ depending on the auction class. And then these are different. These are much better because they're not exponential. Okay. And I'm just going to skip over this slide and just talk about Rademacher complexity now because I'm running a little low on time. Okay, so in order to derive sample complexity bounds, we need to have some way to measure the expressivity of a class of functions. Because just generally, the more expressive a class of functions is, the more samples we need to learn from it. But how do we quantitatively measure the expressiveness of a class of functions? So one idea would be to see how well do functions from this class fit random noise. Okay, so Rademacher complexity kind of defines this, or makes concrete this intuition that maybe we can measure the complexity of a class of functions by seeing how well it fits random noise. So it's okay if these equations don't make sense exactly the first time, but basically what's going on here is that the sup measures for a fixed sample, in the empirical Rademacher complexity, I'm fixing a sample, and the sup measures the extent to which functions in that class can fit to these random noise variables, which are drawn uniformly from -1 to 1, -1 or 1. And then we take the expectation of that noise fitting ability over these random Rademacher variables. And I don't want to define my complexity of a class of functions by a sample. So then the Rademacher complexity, you simply take the expectation over any random draw from the distribution of a sample. And that defines the Rademacher complexity. And so this allows us to prove strong sample complexity bounds. So for example, with high probability, we can ensure that the empirical revenue is going to be close to the expected revenue of any auction in the class. In fact, it's going to be bounded by this right-hand side. And I can make this right-hand side as small as I want by increasing n, so long as the Rademacher complexity of the class is not too large. I can just set it less than epsilon and then solve for n. And so here are just some examples of Rademacher complexity and how so let's just look at the very simple class of all binary, well it's simple but it's very unconstrained, of all binary valued functions. So the Rademacher complexity there is going to be 1/2, whereas if I just look at the very structured class of one binary valued function, the Rademacher complexity is going to be 0, which is as good as we could hope for. Okay, and so we're able to prove that so long as we have at most this many samples, then with high probability over a draw of a sample, the empirical revenue is going to be close to the expected revenue. And I'm just going to go quickly over how, very high level of how we bound this. So the key idea is that this revenue function is a multi-stage optimization problem. So it's unlike a lot of problems we see in machine learning because the mapping from parameter vector to revenue over a bidding instance, it involves this multi-stage optimization procedure. So we're going to split this revenue function into smaller components, which also are like economically coherent. So for example, we can look at the weighted social welfare without any one bidder's participation. That's a component of the revenue function. We can look at the Rademacher complexity of that. And then we can look at the amount of revenue subtracted out to, you could say, maintain strategy proofness, look at the Rademacher complexity of that, and then use these very useful compositional properties of Rademacher complexity and other tricks to combine these separate n+1 many analyses, combine them into one bound of the Rademacher complexity. So for example, one really useful, simple property of Rademacher complexity is that if you have a function class where every function is the sum of two functions from other classes, then the Rademacher complexity of the first function class is just going to be bounded by the sums of the Rademacher complexity of the second option classes. So, so we were able to split up the revenue function and derive the Rademacher complexity and the sample complexity in this way. Okay, so that was affine maximizer options. Yep.
Could you show your theorem once again, which said, how does the sample complexity depend on the Rademacher?
Oh, yeah. This one? Right. So this is a well-known theorem. You could find it in like learning theory books. Okay. Okay, so now I'm going to talk about mixed bundling auctions, which is the simplest. And I think, so we use pseudo-dimension to understand mixed bundling auctions. And I think this is an especially interesting part of the paper because Rademacher complexity is very computational. In order to derive these bounds, you have to do a lot of computationally intensive work. But mixed bundling auctions with pseudo-dimension, which I'll define later, you have to kind of understand the revenue functions at a kind of more combinatorial way in order to derive pseudo-dimension. Hopefully that will be a little more clear. But first, I'll just remind you what is a mixed bundling auction. So we have this valuations instance, and so the class of mixed bundling auctions is parameterized by a scalar C. And we're going to boost the allocations where one bidder gets all the goods by this constant C. So there are n many such outcomes, and we're going to boost them all by C. So in this example, there are two such outcomes, and if C equals 99 cents, then we would boost both of these by 99 cents. And so then we want to know how large must S be in order to ensure empirical and expected revenue are close. And so in order to derive our bounds, we had to look at what happens as you change C, what does the revenue on a single bidding instance look like? And we were able to derive these kind of interesting properties of mixed bundling auction revenue functions. For example, we were able to show that if you increase c, then you're going to have this piecewise linear function with n plus 1, at most n plus 1 many discontinuities, and then once you reach a certain threshold, the revenue function is just going to plateau forever. And the reason for that actually is really simple, because you've increased c so much that the outcome is just always going to be that some bidder always gets the grand bundle of items. So that the auction is actually kind of the same for all c's, constant c's after this point. Okay, and now, so how can we use information like this to derive sample complexity results for mixed bundling auctions? So we're going to use pseudo-dimension, and pseudo-dimension is basically a result, or a very simple extension of VC dimension. So I'm going to remind you of VC dimension, in case you've seen that before, and hopefully you'll see how pseudo-dimension follows. So VC dimension is just a complexity measure for binary valued functions. So for example, so these are functions with range 0 or 1. And so for example, a function in this class might be, one such function class would be the function class of all single intervals on the real line. So a point is positive if it falls in the interval, and it's negative if it falls outside of the interval. And intuitively speaking, this doesn't seem like a very rich class of functions. Because, for example, if I have any 3 points on the real line, I'm never going to be able to find a function that labels the middle one as negative and the outer 2 points as positive. So there, you can never give me an interval that would label a middle point as negative and a positive 2 points as, or the outermost points as positive. So yeah, so intuitively speaking, this doesn't seem like a very rich class of functions. And so VC dimension kind of formalizes this intuition, which says that if I have, give me a sample, and if in my function class, I can pick out 2 to the n many functions where n is the size of the sample, if I can pick out 2 to the n many functions that label that sample in all 2 to the n ways, then this seems like a pretty rich class of functions. And the larger the sample this property holds for, the more rich the class of function seems like it ought to be. Right, so we say formally that f shatters a sample S if for all binary vectors of length n, there exists a function in my class that labels the sample in that way. And VC dimension is just the cardinality of the largest sample that can be shattered by F. And VC dimension gives us great sample complexity bounds for binary valued functions, but our revenue functions are obviously real valued. So how can we extend it? Right, so we have this sample and we have a class of functions mapping, say, from negative u to u. And I would still like to use this notion of a binary labeling, but I can't just say that if a function on evaluated on a sample gives me a binary labeling, because these are no longer binary functions. So instead, I'm going to introduce a vector of thresholds, R1 through R9. My sample is of size 9, let's say. And I'm going to say that if you give me a function, that function evaluated on a sample, that function evaluated on x is labeled as 0 if it's less than its threshold. And f evaluated on x is labeled as 1 if the function is greater than its threshold. So in this way, I can label my points using a binary vector. And if you can give me 2 to the n, again, functions in your class that label the sample in all 2 to the n possible ways using this fixed vector of thresholds, then we'll say again that f shatters S. And pseudo-dimension is the largest sample, the size of the largest sample that can be shattered by F. And Here's just an explicit connection between pseudo-dimension of a class and the VC dimension of a similar class. Okay, and it gives us great sample complexity bounds. For example, if I need at most this many samples to ensure that expected revenue and empirical revenue are going to be close with epsilon, by epsilon for every revenue function in the class. So, okay, now back to mixed bundling auctions. How can I use pseudo-dimension to understand mixed bundling auctions? Okay, and just to remind you what again is a mixed bundling auction, I have these n outcomes. One bidder gets all the goods, the grand bundle, and we boost all those outcomes by some parameter c. And so we were able to show that the class of n bidder m item at mixed bundling auctions has pseudo-dimension log n, which is interesting, especially because this bound doesn't even depend on the number of items. But what I can show, basically proof by pictures, is that if you only have 2 bidders and an m item mixed bundling auction has pseudo-dimension 2. And so I'm going to give a proof sketch. So the fact we show this, that there exists a set of 2 samples that can be shattered by the class of mixed bundling auctions. And now I need to show, in order to show pseudo-dimension equals 2, I need to show that no set of 3 samples can be shattered. So let's suppose for a contradiction there exists a set of 3 samples that can be shattered. And remember, these samples, they're bidding instances. So they're the concatenation of 2 vectors, the first of which is the bidder 1's valuations for goods, and the second of which is bidder 2's valuations for the bundles of goods. And so what does it mean to be shattered again? It means there exists this threshold vector and 8 MBA parameters such that the corresponding auctions on those 8 parameters induces all 8 binary labelings on S with respect to this threshold vector. So for example, maybe the revenue of the mixed bundling auction parameters by C1 achieves revenue less than R1 on valuation vector V1, less than R2 on valuation vector V2, and less than R3 on valuation vector V3. So the binary labeling is 0, 0, 0. We can do this, all 8 binary labelings, if indeed S is shatterable. And now just believe me again that the revenue function is going to look like this. There is this section with a slope of 2, and then it plateaus off forever at some C sub I. So if you believe me, I'm going to move on. And now we can split this into 2 cases. Either the threshold is less than the plateau, or it's greater than the plateau. Let's just assume for now that it's less than its plateau. The second case is basically symmetrical. Okay, and remember we have these 8 MBA parameters. And we know that if we fix V3, for example, we know that 4 of those MBA parameters are going to fall in this small region because 4 of them label V3 as 0. 4 of them induce revenue less than the threshold. So this is the C-axis, so so 4 of those C parameters must fall in this small region. And now I can flatten this representation. There's going to be this region where the revenue on V3 is increasing as we increase C, and then the revenue plateaus. And there's no reason I can't order my sample such that C2 falls after C3 and C1 falls after C2. And I know the revenue is going to look the same on all of these valuation vectors. So there's going to be this region, again, where it's increasing, the revenue is increasing, and the revenue plateaus. And I can impose my coloring onto this representation. So the red means that revenue is less than the threshold. Green means it's above the threshold. And I know I can color the other 2 in similar ways. I know there exists R2 and R1 such that the coloring also there's going to be a region where the revenue is less than its threshold and a region where the revenue is greater than its threshold. But I know since the revenue function is increasing in this boxed region, I know that the revenue is increasing, so I can move from red to green, but I can never move from green to red. Okay, but let's think about what does the binary labeling look like here. In this region, the binary labeling is 0, 0, 0. The revenue is always less than its threshold on all 3 samples. The labeling here is 0, 1, 0, and the labeling here is 0, 1, 1. But we're missing one labeling, right? Because we know that if this sample is shatterable, then there has to be somewhere in this region, there has to be a labeling 0, 0, 0, 1. That's what we're missing. But if we were able to get such a labeling, it would have to be that the revenue dipped back below its threshold, somewhere in this region where I know the revenue is increasing. So that's impossible. So we reach a contradiction. There's no way the coloring could look like this. It's impossible, so we know that no set of 3 samples can be shattered by the class of mixed bundling auctions. Okay, so we get our pseudo-dimension result, and that allows us to bound the sample complexity of mixed bundling auctions. And so in summary, what did we see? We analyzed the sample complexity of these hierarchy in the hierarchy of auction classes, and along the way we saw structural properties. Hopefully this final proof gave you some idea of some of the structural properties we were able to glean from our investigation into the pseudo-dimension and Rademacher complexity of these auction classes. And we hope that this is of independent interest beyond the sample complexity results. For example, we think that maybe these structural insights could also aid with optimization algorithms for optimizing over these auction classes. So that's everything. So if you have any more questions.
So what's known about how good MBA auctions are in terms of the revenue they give versus the optimal auction?
So Thomas did some experiments with this, and I think oftentimes you could exceed, for example, the baseline VCG margin by a significant amount. Yeah, I don't know the numbers off the top of my head, but normally they did pretty well.
I can tell one thing which is kind of surprising. Even if you have 2 items for sale and no complementarity or substitutability and 2 bidders, both are drawing valuations uniformly 0, 1 for each of the 2 items, the optimal auction is not a mixed bundling auction with reserve prices. The difference is tiny. You can actually get a tiny amount better, less. The difference is way less than 1%. But the optimal auction, even in that simple setting, it's not a mixed bundling auction with reserve prices. Also, it's not separate auctions of the items, which is way worse.
Let's take the rest of the questions offline. Thank you.